Alright, so in this video we go over section 6.4, graphs of the sine and cosine function. So in this section we are going to look at graphs of the form a sine omega x, a cosine omega x. Well, where a is going to be the amplitude and omega, well, that's the quantity that will be related to the period of the function, which is actually the value of x in which the graph completes one cycle and then it repeats itself. Then we're going to learn how to graph this kind of functions using key points, well, and finally do the reverse given the graph, obtain the actual function. Okay, so let's make a table of values here. Well, so in this case we have the function f of x equals to sine of x. And I'm going to make a table of only the representative values. Of course, there's more that we can fill in right here. So I'm just going to fill in this blank like just like 0, f of 0, or rather sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. These values, of course, you can get them from the unit circle. Sine of 0, sine of pi over 2, sine of pi, etc. Alright? So what are we going to do this? Well, this is, of course, x, f of x is always y. Where I'm going to plot this point. So this is going to be 0, 0, pi over 2, comma 1, pi comma 0, and 3 pi over 2 comma -1, and 2 pi comma 0. And well, we're going to connect these dots using the graph. Of course, it's not going to be a diagonal or a straight lines. Actually, it's a smooth curve right here. Okay, that's at the first half of the cycle, and that's the second half of the cycle. Of course, if we keep going, this graph is going to repeat itself forever and ever. Right, what are the properties of this function and this graph? Well, the domain, it's all real numbers, right? Well, in this case, I'm just graphing only one period. But if you were to graph the entire function, for example, let me clear this. Let me type y equals to sine of x. Okay, and close parentheses, and let me hit graph over here. It's gonna graph one period, another period, and so on and so forth. It's gonna go on oscillating forever in the positive direction and as well as in the negative direction. Well, here I have a different window, and it only shows the positive, the right side of the Cartesian plane. So the properties, well, the domain, and that's why the domain is a set of all real numbers. We don't have any asymptotes, we don't have any holes, etc. And the range consists of all real numbers between -1 and 1. If you look at it, well, the lowest point is -1, the highest point is +1. It's an odd function, and that means its graph it's symmetric with respect to the origin. Well, let me actually show you another. Let me edit the window here. So I'm gonna go for the x min instead of 0. I'm gonna go -2 pi, and I'm gonna change that to 4 pi. No, actually 2 pi. All right, that way you can actually see when you look at the graph, because I just did by hand only the positive side. If you look at this, if you focus on the origin, you can see the graph is symmetric to the origin. Actually, that is, if you rotate the graph 180 degrees, you obtain the same graph again. All right. Well, the x-intercept, the period is 2 pi. That means it completes another cycle. It repeats itself every multiples of 2 pi. The x-intercepts are 0 and multiples of pi. And the y-intercept is the origin as well, is 0. The absolute minimum is 1 and occurs at x equals pi over 2 and then 5 pi over 2. But in this case, I don't have 5 pi over 2, but it would go pretty much this way. All right, if I did, this would be 5 pi over 4, over 2 rather. The minimum is -1 because that's the lowest value in the domain. And it occurs at 3 pi over 2, which is right here, and 7 pi over 2, 11 pi over 2, -pi over 2. If I went back right here, this would be -pi over 2. All right. So, and that's pretty much the bigger picture for the graph of sine. Of course, these graphs, just like the ones that we did in chapter 2 at the beginning of the course, these graphs as well suffer other kind of transformations. And again, I brought back this summary of shiftings, and well, in this case, all we're gonna look for this section at least is scalings, vertical and horizontal scalings, and shiftings with vertical shifts, as well as reflections. Of course, the horizontal shifts, we're going to leave those to the end of the chapter. In this case, those are called phase shifts. You'll see. So in this case, graph y equals 3 sine of x. What are the transformations involved? Well, the only one transformation involved is we have a vertical scaling by a factor of 4. In other words, from the key points that we have here, focus only on the y values, where for a vertical scaling by a factor of 4 implies to multiply all the y values by 4. All right, for example, this is the point, the origin 0, 0, and this is pi comma 0, and this is 2 pi comma 0 right here. All right, so well, all we focus is on multiplying all the y values by 4. So I'm going to go times 4 only this guy, times 4 only the y, times 4 only the y value, times 4 only the y value. So what's going to happen here? Well, so in this case, what we do is the x's remain the same. Notice I didn't change in the provided graph. I didn't change the scaling. They are the same. So in this case, 0, 0 remains the same. Pi over 2 comma 1 becomes pi over 2. 1 times 4 becomes well, not 4, by the way. Actually, I did a silly mistake. This is by 3. 3, not 4. Okay, it's 3. So that becomes pi over 2 comma 3. Pi, which is pi 0, still pi 0, because 0 times 3 is 0. And then 3 pi over 2 comma -1 times 3, that goes to -3. And well, 2 pi is somewhere here. So what it does is, it's only a vertical stretching in this case, or vertical scaling. If you want to see it on the graphing calculator, of course, let me second quit. For some reason, it's not. Okay. Or is it this one? Well, let me go back to simply, let me just put 3 sine. Is that 3 sine? So I'm gonna do 3 sine x. All right, and let me change the color. Let me change this to green. Okay, and graph. So what it's going to do, essentially, it's the same graph, the same intercepts, but it's only stretched by a factor of 3. All right. This way you can see the difference between the original and the one I did by hand, because I mean right here it's not very clear, the difference when we do it by hand. The idea is to understand ultimately the transformations that are involved. Let's look at example 2. Well, this first transformation here, this negative, involves our reflection about the x-axis. In other words, what the negative does is flip the graph, or change the signs of the y values. So what I'm gonna do here is, let's see, this 0, 0 remains the same, of course. This pi over 2 comma negative 1 becomes pi over 2 comma 1, flips side. This one flips side over here. This one remains the same because 0 times negative 1 is 0, and then pi over 2, 3 pi over 2 becomes over here, and then 0. So this one. So this is the graph that we obtain. For now it looks like this. All right, let me show you that on the graphing calculator how this looks like. Let's see, let me see if I can. Yes, because it's too bright. Oh, it's all actually all the light. Well, so this is, let me edit this. I'm gonna make this insert negative, and let me delete these 3. Negative sine x, what it's gonna do, okay, it's gonna give me the original sign. And next, what it's gonna do is the graph basically flipped. All right, which is what I have. It's pretty much upside down, all right, with respect to its original. Now, the next transformation that occurs in this case is this 2 right here, which essentially reflects this idea right here, which is a horizontal scaling. So the function being multiplied by some number times x, well, a number times x, we divide the x coordinates by b. In other words, it's a horizontal scale. Horizontal scale. And in this case, by a factor of b. So in this case, what we do is divide all x coordinates by b. That's how the graph is it's being affected. In other words, this pi over 2 becomes a pi over 4. All right here. This pi becomes a pi over 2. This 3 pi over 2 becomes a 3 pi over 4, and this 2 pi becomes a pi. That's actually, oh well, that goes up here, and yeah, not here. And this 5 pi over 2 becomes a 5 pi over 4. This becomes a negative 5 pi over 4, and like this. So that's what it does. So it basically, what it does here, for now, let's just leave it like this, and let me show you that in the calculator. It would be better if we edit this. In this case, it's a 2x. Okay. When we put them together, so that's the original, and then that's the compressed. It actually does more cycles, all right, with respect to the original graph. All right, let's look at graph of cosine. The graph of cosine. So for the cosine function, let's fill in this table. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2, that's a 0. And cosine of 2 pi is 1. Okay, let's graph this. Let's plot this point 0, 1, pi over 2, 0, pi, -1, and 3 pi over 2, 0, and 2 pi, 1. So the graph is going to look like this. That's over one period. It has essentially the same shape as the sine function. However, we will find out that it is only shifted pi over 2 units. So let's graph this. Let's graph cosine just so you can see a little bit more of the graph. Well, essentially the same wave, but it looks different. Now it has a y-intercept at 1. Everything is shifted pi over 2 units. So let's look at the properties. Well, the domain is also real numbers, all real numbers, and the range goes from -1 to 1, and in this case, well, it's the graph is an even function. That's one of the key points for the key properties. Cosine is an even function. If we go back to the graph right here, can you see right here that the graph is symmetric about the y-axis? Well, that's because it's an even function. The period is also the same, pi of 2 pi, but in this case the x-intercepts are a little bit shifted pi over 2 units. The y-intercept is 1, 0, 1. All right. And the absolute maximum is 1 because that's the largest value of the function in the range. And those values occur when x equals to 0, x equals to 2 pi, and if we graph more another period, it would go to 4 pi, 6 pi, etc. In other words, even multiples of pi. 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, etc. and in the negative direction as well. And the minimum is -1. That's again the lowest point in the range. And those occur when x equals to pi, when x equals to 3 pi. All right, 3 pi. And actually, I think I had a little typo. This one should have been a negative pi, by the way. All right. So let's graph a couple of functions right here and identify the transformations. And in this case, well, these two right here will do a vertical stretch by a factor of 2. In other words, all the y values are going to be multiplied by 2. Well, 0, the 0 times 2, we don't really need to do that because that's still going to go 0. So what we're going to get is, well, 0, 2, in this case 0, pi over 2, 0, pi -2 as opposed to 1. Okay, this is times 2, times 2, times 2. And 3 pi over 2 right here. These points remain the same. 2 pi times 2. All right. And that's how it's going to go. All right, just over one period. Now, what about this this 3 right here? In this case, that's going to be a horizontal compression, actually, or scaling. I'm gonna call it compression. In the other example, I just said scaling with it, but the correct term right here in this case, because we are going to divide by a factor of b, in this case by a factor of 3. This is a horizontal compression by a factor. Over here I should have said a factor as well, by a factor of 3. All right. So all these points, what we need to do is divide all x's by 3. That's what we're going to do. So this is pi over 2 divided by 2, by 3 rather, is going to become pi over 6. This pi divided by 3, it's pi over 3. 3 pi over 2 divided by 3 is pi over 2. 2 pi divided by 3 is 2 pi over 3. 5 pi over 2 divided by 3 is 5 pi over 6. So essentially the same graph, but what is going to change here is the labels here. All right. So let's just draw it over one period. Well, a little bit more than one period. It's right here. The period is going to be 2 pi over 3. We're going to see about that in a minute. Now, well, again, it'll be better if we put this together, the two graphs together. In this case, y. In this case, we have cosine and 2 cosine of, in this case, 3x. All right, and then graph. Notice in this case, because the x's are the x values are divided by 3. Well, it's a compression. The graph is compressed, as opposed to the previous example that we did for the sine function. All right, let's do determine the amplitude and the period of the sinusoidal function. Well, when we have a function of this form and that form, which in this case basically the sine and cosine with its horizontal compressions and vertical compressions only, well, the absolute value of whatever number multiplies the function is going to give us the amplitude, and the amplitude is pretty much a measure of how high does the function go, or in how low does the function go. For example, let's determine the amplitude and the period for y equals 3 sine of 4x. Well, so the amplitude, which is defined as the absolute value of a, in this case, this is a, and this number that multiplies the x is omega, not w. It's a more curvy w. Well, that's omega from the Greek alphabet. And in this case, the absolute value of 3 equals to 3. So this means that the sine function in this case is going to have a range between -3 and 3. That's what the amplitude is going to tell us. For the period, which is 2 pi divided by omega, which is the number that multiplies the x, that's going to be 2 pi over 4, which reduces to pi over 2. All right, what does that mean? This means that this sine function is going to have one turn at pi over 2. Okay, let me just so you can see this a little bit more clearly. Let me go back to sine of x, and in this case I'm going to do 3 sine of 4x. Okay, I'm going to edit the window here. All right, I'm going to edit the window, and I'm going to draw only one period right here. So I'm going to go from 0 to 2 pi. It was already 2 pi, and the x scaling, in this case I'm going to scale this by, I'm gonna have every single little line to be the following. Well, I'm gonna do it not pi over 2. I'm gonna do pi over second pi over 4. Pi over 4. It's going to represent a pi over 4 every single line. And let me hit graph right here. Well, the range, the y values are going to go from -5 to 5, which is fine. That's all we need. What's going to happen here? Well, look, that's one period for the sine function. And look at that, 1 period, 2 periods, 3 periods, 4 period. That means that the function 3 sine of 4x, this 4 means that this sine function oscillates 4 times as in its original unshifted or uncompressed function. So with respect to sine x. So 3 sine of 4x oscillates 4 times in the same amount of space in which sine x oscillates only once. That's pretty much what the period is, if you will. Okay, let me leave you with the picture again. All right. So now let's graph sinusoidal function using key points. Well, there's a really nice procedure here that that asks you to divide the interval into 4 sub-intervals of the same length. I will sort of do that in the way I do this. And all you need to do here is to recall or memorize the shapes of y equals to sine x and y equals to cosine x. That's all we need to do. Memorize those functions. And then from here, you plot the points. All right. Something I didn't really mention when I was graphing the other function. Let me go back real quick to the previous example, and I didn't mention this, and it's going to be important when we move on to the next examples. So really, these trigonometric functions have what they call a line of equilibrium. That means this line that makes it in a way symmetric, if you will. You know, that the one that divides the graph into, all right, like over here it also, there is this invisible line that you don't have to draw, but it works as a reference when it comes to drawing the graphs of this kind of functions. How are we going to use that? Well, you'll see in the examples that I have here. All right, graph y equals 3 sine of 4x. Well, we already did. All right, we already did in the graphing calculator. And let's take the domain and the range. Well, we're gonna graph this using finding the period and the amplitude. Well, the amplitude is 3. We already figured that out, and the period we already found out that the period of the function is pi over 2. All right, that's the period. I'm not going to repeat the calculation. If you want to see how did I get that, go back to example 4 in the previous page. All right. So that means that the graph completes one cycle at pi over 2. So in this case, let's see, that's pi over 2. Originally, this is pi over 2, pi through pi over 2, and 2 pi. Well, not anymore. This is going to be pi over 2. All right. And then I'm going to divide this in 1, 2, 3, 4 essential parts, or 4 equal parts. Well, this is halfway through between the origin and that point where the graph completes one cycle. So if it's halfway through, this is half of pi over 2, which is pi over 4. And then halfway through these 2 points is half of this value. So pi over 4 times 1/2, that's a pi over 8. And well, to figure out this, the value between pi over 4 and pi over 2, just add to the value in the middle the value right here, which is pi over 8 plus pi over 4. Well, that's going to give us 3 pi over 4. How to do that in the calculator? Well, omit the pi symbol so you don't get fractions. So I'm going to add 1/4 plus pi over 8. Well, 1/8. And well, let's frac it. And that's 3/8. Or 3 pi over 8 rather, not 4. Alright. Well, in this case, it's going to inherit the same shape as in the original sine. However, in this case, because of the amplitude being 3, all the y values are going to be multiplied by 3. Well, in this case, except the x-intercepts, because at the x-intercepts the y value is 0 and that doesn't get affected really. So well, in this case, 3 units, negative 3 units, 0. Oh wait. Oh, actually here and here, not this one right there. Never mind. That's only an x-intercept. And all we do is that's one cycle. Alright? And if we go back to the original graph, okay, if we go back to the original graph, let's find one of the x-intercepts. So let me go and erase this and clear this one. I just want this graph. Let's find what the intercept is, just so you can see that. Okay, second calc. I'm gonna find the the 0 actually, not the intersection. And well, for example, let me just go. So let me from here and there. Let's find the 0. Well, in this case, y equals to 0 and x equals 1.5707. Okay, 1.5707 is the same as pi over 2. All right, which is where it completes the first period. So pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and then pi. 2 pi. Let's do another example, example 6. Y equals to sine of negative pi over 2 times x. Well, let's take the domain and the range over here before we leave. Well, domain. Well, there's two ways to express the domain. Well, negative infinity to positive infinity, or the fancy x belongs to all real numbers set notation. That's the other way. And for the range, because the amplitude pretty much dictates the range, so that's in this case, well, closed, -3 to 3 enclosed. Or alternatively, y such that -3 -3 less than or equal y less than or equal 3. All right. Let's do the next one, and well, it's gonna be a little bit weird when it comes to the number that multiplies x and the negative sign. But again, keep in mind that in the previous section we went over what to do with these negative signs inside of parentheses of sines and cosines functions. So because if we keep in mind that sine actually it's an odd function, well, in this case this sign is going to go outside. So if we rewrite the function y equals -2 sine of pi over 2, which multiplies x. All right, and then, well, let's find out what the amplitude is. In this case, the absolute value of -2. The absolute value gets rid of the negative sign. So the function is going to oscillate between -2 and +2 in the y direction. And for the period, which is 2 pi divided by omega, which is the number that multiplies the x. In this case, let me highlight that with yellow just so you can see what am I plugging in and where. So 2 pi divided by pi over 2. Okay, be careful here. We are dividing by a fraction, which is the same as multiplying by the reciprocal. Dividing by pi over 2 is the same as multiplying by 2 over pi. And in this case, the pi's go away and 2 times 2 equals to 4. Alright, what is this going to mean? This means that the graph of sine will have a period of 4. So that means 1, 2, 3, and 4. Alright, halfway through is going to be half of the period. Well, in this case, for integers like this, it's really easy to get the labels. Alright, 5. -1, -2. Okay, what's going to happen here? Well, number one, on the one hand, this negative is going to essentially flip the graph. Instead of having to go up, down, and up again, it's going to make it go down, up, and down again. So it is in this case. But instead of going 2 units as the maximum value, that's going to be -2 units, 0, 2 units, -2 units. Alright, and actually here. Not there again, I made. Alright, don't need this. Alright. And that's how it's, oops. That's essentially one period up to here. Of course, I'm just going a little bit more. All right, you don't have to. That's fine. Okay, let's do this in the graphing calculator. So first, I'm going to have, what is that sine? Okay, is that sine again? Sine x. And let's clear, that's going to be 2 sine of -2 pi over 2 x and close parentheses. Do not graph yet. I'm going to fix the window to have x to go from 0 to 4 in this case, because that's where it completes a period, and well, there's x scaling to be 1 each. The y mean, that's fine, don't worry. Okay, that's what I'm going to have. I don't think it's going to work in this case. Well, yes, that's fine. Alright, it completes 1 cycle. The shifted one completes 1 cycle every 4 units, as opposed to the original one that it completes the cycle at 2 pi unit, which is 6.28, roughly 6.28 units. Alright, let's take the domain and the range. Well, the domain, again, it's all real numbers. -infinity, +infinity. And the range, I'm not going to do both notations. Well, actually I will. X such that x belongs to the set of all real numbers. And the range is going to go from -2 to +2. So that's actually brackets, -2, +2, and y such that y is greater than or equal -2 or less than or equal to +2. And let's look at the very last couple of examples. Well, we're almost done over here. Let's do another one. This one is going to involve not only vertical stretchings and horizontal compressions, but this time it's going to involve uh, vertical shiftings, in this case 2 units down. Well, before I move on, I just want to recall that there is some sort of invisible equilibrium line that is going to be a little bit different for this example we are about to cover. So, well, number one, let's state first of all the transformations in here. Well, let's see. I'm gonna use this time. I think I'm gonna use a pencil instead. So, well, first of all, let's state the amplitude, which is the absolute value of A, or the absolute value of 4, which happens to be 4. That means the graph is, be careful in this case, potentially oscillating between -4 and 4. But it's not going to be the case because there's some vertical shifting that it's going to affect that a little bit. All right. So in this case, well, the period, which is defined, as 2 pi over omega, which is the number that multiplies x inside of the parentheses of the trigonometric function. That's going to be 2 pi over pi, which reduces, in this case, pi's go away, and the period is 2. All right, that's going to be an interesting one to graph. Well, what's going to happen here? Well, so originally there's I'm gonna scale this to 2. Okay, to 1 each. And well, initially, let me skip the -2 part right here. So that's I'm gonna call this. Let me label this as pi over 4, pi over. Oh wait, not pi's. In this case, there's no pi's involved. Oops, there's no pi's involved in this. Only let me use just fractions: 1/2, 1, 3/2, and 2. All right. Originally, well, for cosine in this case, which starts at 0, 1. Well, I'm going to use pencil in this case. It would look like this. All right, it would look like this. That's one period for cosine. However, well, in this case, what we need to do is to stretch these y values by a factor of 4. All right, 1, 2, 3. Well, 4 would be over here. Let me erase this. I'm going to do this just on top. 1, 2, 3, 4. It would look like this. All right, in this case, let me erase. Oh, I don't want to erase this. It's gonna be a mess. So, well, actually, I have to do it. And in this case, well, this -2 will shift all these points down 2 units. And all right, and also remember that horizontal dashed line here that I drew you before. I'm going to shift that horizontal line, which is our baseline or equilibrium line. Well, I called it equilibrium line. This time I'm going to refer to it as the baseline. Well, in this case, it's going to have these points right here, and that's of course going to be 1 period for this particular cosine function. Well, let's put it on the graphing calculator. So let me actually zoom. Let me do standard zoom this time. And oh, I shouldn't have done that yet. Well, I won't be able to do this one until it's graphed. All right. So this is, well, I'm going to graph the original cosine function along with 4 cosine of delete and then minus 2. Okay, it's going to draw the original and see how it's slightly shifted down and also stretch it, and it's also stretched vertically, so it's taller, but it's also skinnier as opposed to the original function. But the domain in this case, all right, is domain. The domain is in this case again all real numbers, or x such that x belongs to all to the set of all real numbers. But the range right here, well, it's going to be changed right here by looking at the graph. Well, it's going to go in this case from negative 1, 2, 3, 4, 5, 6 to positive 2, or y such that y is bigger than or equal negative 6 and less than or equal to 2. Now, another way to find the range. Okay, so consider this cosine part as your f of x. All right. We're going to get the range of the function by means of a compound inequality. Well, we know that the cosine function has a range from negative 1 to 1. All right, which in this case is the same as f of x. But in this case, notice this f of x is being multiplied by 4 and subtracted by 2. What I'm going to do is set for f of x minus 2 less than or equal 1 greater than or equal negative 1, and I'm going to solve this for f of x. So what we do is add 2 to this well, not actually 3. No, that's not going to be, that's not how this is going to be. It's actually the reverse instead. Actually, let me see if I have here that in my notes. So I remember setting this up in a way of a three-sided inequality, but I can't find my notes. Okay, what we can do is start with the same inequality. Never mind, I got it. I found my notes. F of x goes from negative 1 to 1. What I'm going to do is multiply the three sides by 4 to have that for f of x. These 4 right here. And that's going to give me negative 4 less than or equal for f of x less than or equal 4 times 1, that's 4. And then I need to represent this negative 2 in a way, and all we do here is subtract 2 to the three sides, which is going to give us negative 6 for f of x minus 2 and 4 minus 2, that's a 2, which is exactly this same range. All right, so our starting point is that cosine goes from -1 to 1, and then do the transformations in a very similar way that we did in chapter 2. All right, so now we're going to do the reverse, which is obtain an equation for the functions represented in each of the graphs. All right, so in this case, this first function makes me think that this is a cosine function. How do I know this is a cosine function? Well, because the graph is symmetric about the y-axis, which is an even function, and we know that the cosine function it's an even function. So that's how I can think of a cosine function. All right, so let's see. I need to find the amplitude by looking at the graph. Well, notice how it goes from -4 to +4. That means the amplitude is 4. Now, I need to focus on only one period of the cosine function, and if we look, it completes one cycle at 4 pi. That means a period, which is 2 pi over omega. Now we need to figure out the omega value by setting this. We know that the period is this guy right here. It's this p, and that's 4 pi. 2 pi over omega, and you might want to solve this by cross multiplication. Multiply both sides by omega, divide both sides by 4 pi. 2 pi over 4 pi. The pi's go away, and 2 over 4 becomes a 1/2. All right. So in this case, the function that we're looking for is indeed y equals, well, a cosine of what is this going to be? Omega x. We're looking for the function y equals to 4 cosine of 1/2 x. All right. Final answer. Let's look at the other one. Well, the other example also makes me think of a cosine function, because we have a graph that is symmetric about the y-axis, which makes me think it's an even. It represents the graph of an even function. However, notice this one is in the negative side, as opposed to the previous example. Yet we can figure out the amplitude, which is 3, because it goes from -3 to 3. But now what about the period? Well, in this case, let me do one cycle. The fact that the graph is upside down, that tells me that the graph it's going to have a negative sign in between. All right, so let's see what is the value at which the graph completes one cycle? Well, that's 4. So the period, which is 2 pi over omega, that's 4 equals 2 pi over omega, and omega equals to 2 pi over 4, which is pi over 2. Alright, so in this case, let's write the function y equals to a, again, cosine of omega x. And in this case, that's going to be, 3 cosine of pi over 2 times x. But in this case, because of the graph being reflected about the x-axis, in other words, it's upside down, we need to have a negative sign in front of it. Final answer. And this is a good place to quit. I will see you in the next video.